Okay, so welcome back. Now our goal is to define full value semantics for the LDL and finite words, which we call F, and we call the resulting logic F(L)4. So what's the main idea? So let's check the formula next day. And in the first position, what things will happen? Well, we cannot evaluate next day because we don't know what the next position is. So in the two-value logic, we would go for false. Now our aim is easy. In the full-value setting, we say, well, we cannot really evaluate next A now completely, but if we would have to do it, then we would go for false. So we go for presumably false. So we don't go for false. We say, well, if the word would be terminated now, it's false, but it can continue, and then we might change our mind. So for example, here if we have next day and we have seen two letters, we go for false. And here, when we see the second letter not satisfying A, we go for false. Here we know that we have a real false. If the second letter coming after the first one would contain A, the next A would be true. See, here we swap our mind. And in full-value logic, the idea is to go for true. Well, we swap our mind from the presumably false and we go for true, but not, we don't change the wording false. And for the weak operator, it's similar. Yeah, here nothing comes after the first letter, we would go for true. But in the full-value setting, we go for presumably false. Now, how can we create such a semantics? I think we can. Basically, skip that. Now we go to these slides. So the idea is very simple. True is true, false is false. For the atomic propositions, we look into the first position, just as we do to find the LDL. The Boolean combinations, we do it as before. If we want to check whether phi or psi is satisfied by word W, well, we check whether phi is satisfied by W, or to which extent it is satisfied, and to which extent psi is satisfied, and then we take the best out of it. We take the join. And for the conjunction, we do the same stuff, but we take the mean. And what about negation? So to which extent is W satisfied not phi? Well, let's check to which extent it satisfies phi. And then we take the dual value. So basically we do the same stuff for the two-valued LTL as well. It's exactly the same stuff. The only difference now is for FLTL, for the next operators. So what will we do in the two-value setting for next phi and W? Well, we check whether the length of W is greater than 1, then we check phi on the remaining part of the word. And here we go if the word just consists of one letter. Yes?
The EU is about to the previous slide.
Yes.
So for the second case of disjunction, suppose that I take the formula globally A for eventual root of A.
Yes.
And now if so this value is true, right?
No. Does not.
In the semantics.
In the semantics, it
Does
does not.
But the formula value is true. I mean, semantically equivalent should be true.
No, we define the semantics here. So you can say you don't like the FLTL4 semantics because intuitively this is true. But if you compute the semantics according to these semantics, it won't be true.
Right, so it means that I can find two equivalent formulas that have the same.
You can find formulas that are equivalent to the two-valued semantics that are no longer equivalent to the four-valued semantics. And this is a very fair critic point. So, what is the reason for that? The reason for that is you check something individually, and here as well. So, we say, let's check phi separately, and let's check psi separately, and let's forget about the combined meaning of that. So what can happen is that we, for one part, we get don't know, and for another part, for this psi, we also get don't know. It's presumably true, it's really false, or something like that. But if somebody tells you don't know and the other guy also tells you don't know, then the only information that you have is don't know. But if you would look at the formula completely, then you would know the answer. And that's one of the drawbacks of this logic.
This is why you use automated-based analogies.
Yeah, I wouldn't say so. This is why we use LTL3 as a different approach. But it's not only, we come to automata in 5 minutes also for this logic. But we come with automata that have the same deficit. So what happens here? So if you look at the complete formula, this formula is equivalent to true. So according to the two-valued semantic, that means you could remove it and substitute it by true. Or in an automata setting, you could analyze that if you have the right automaton model, then whatever comes, you cannot falsify this formula anymore. And you could take this information into account, and this is what brings us to the notion of anticipation. Anticipation means, well, don't look and evaluate on what you see, also look on what you're going to evaluate. If you're going to evaluate such a formula in the future, and you cannot violate it anymore, then already say the result before. But we will see that maybe tomorrow. So, if you want to spot the differences of these of FLTL2 and FLTL4, it's only in this situation where we have a difference. If we are at the end of the world, if we are at the end of the word in FLTL2, in FLTL we would go for false. Here we are less restricted, we are a little bit more restricted and say presumably false. And the rest goes through. We could also come up with a definition of semantics of until. We don't want to do that because what should be the right semantics of until? It should be the semantics that we can use the unwinding rules. Yeah, so we want, here we basically gave the definition that makes sure that we can use the unwinding rules. We can do the same for release. We can do the same for eventually and globally. But the main idea is the equivalence, phi until psi is equivalent to psi, or phi and next phi until psi should hold. So now, equivalence of formula is defined in the very same way. The formulas are equivalent if they lead to this, yield the same truth value for every possible word. possible word. Now let's come to monitor functions. And the monitor function that we're going to build here is that we want to evaluate our work from left to right. Yeah, so we see the system running, and once we get a new state, we want to process it using our monitor, and then we wait for the next state, and then the next state. And so on. In the previous sample, we had the finite trace given, and we was not, but we also processed it from left to right, but it was not so important because we could also maybe from backwards and so on, whatever is suitable, because we have the whole trace given. But now we are looking at a system that may run for years, and we want to check continuously what happens. So we want to have a monitor procedure going from left to right. So it takes an LTL, formula and a letter A, and it performs a formula rewrite. So it should return the semantics that we get by remembering the whole history and the current A. And we also get a new formula back that tells us what to check in the next position. I think we go directly into the code. So the procedure is called eval FL04. So we get a letter, we get a formula, and we produce the current truth values, and we produce a new formula that we're going to check in the next step, for the next letter. So we apply the function to a letter A and the formula, and we do it in a recursive fashion. So if we will have to check the formula true, reading some letter A, well, everything is fine, we return top. And yeah, what can you check in the next state? We'll have to give back something. We give back true here. False, we have lost, and we'll return false. Maybe let's ignore these formulas for the moment. So you get an action A, and you have to check proposition P. So you check, is P true in the current position? If so, we return top. If not, we return false. For the negated proposition to the due. What do we do for or intent? Well, we have this A, and we should check phi of psi. So we run the procedure on A and phi. We run the procedure on A and psi. We get a truth value V phi here, and we get a truth value V psi here. And we take the join because we have to evaluate the node. And for the end, we do the dual. We call these functions intake, commit. We come back to the second components. So what do we do for next state? For next phi? So we have the current word, and we want to check next phi. Well, we don't know whether there is some future extension. If the whole system crashes, then there is no next letter. So for the strong next, the current truth value would be presumably false. But if the word continues, what should we check? The word continues, what should we check? Well, we should check phi. We're checking next phi for the current A, and if we continue, we should check phi. So that's the main idea. So we return the current truth value for the given A, and we return a formula that we should continue to check after the current position. And for the weak next phi, well, if we continue, we also have to check phi. And the current truth value is presumably true. And what do we do with the temporal operators? Again, we These are easy. If you want to check until release point, we just call it with the unwind. So, if you read a letter and we have to talk about the second position, well, we cater for the fact that there might not be a second position, but if there is, we continue with the file. And if we go back to the previous slides, well, this could be, you can think of it, this could be like an X formula, this could be an X formula. So that would mean that we get the truth values here, and we got the information what we should check in the next state, and we are interested in the disjunction of these two formulas. So we take the A to rewrite phi and get an answer what we should verify starting from the next position. We get the rewritten version of psi, this psi prime, this is what we should check in the next position. And we combine these two using disjunction. So that's the formula that we continue to check starting from the next step. Alright, so this is why it's a little bit more complicated. Okay, so that's, maybe go through an example. So we read this A, we want to check globally A. So we are reading this A, and we have to check A and tweak next globally A. That's the unwinded version of this globally. So this is a conjunction, so we have to check A. We have to check A whether it falls in the first position. Of course it does. And we have to return formula, so we return true. We have to check weak next globally A. Reading this A, this means presumably true, and we have to check globally A in the next position. So we get true and presumably true, presumably true, and the formula that we have to check is true and globally A. So right now it looks good, and we'll continue checking globally A, starting from the next position. That's what we expect. And if we continue reading these, then eventually we see that converge does not satisfy. Then we skip this example, the second one, and we now go to mean emissions. So, why do we do this? So let's go back to this formula. Whenever we read a letter here, we do a recursive descent over the whole formula. This is very costly to do that at runtime. We manipulate our formula data structure, we build new formulas, and we do that at runtime. So doing formula rewriting at runtime is not a very good idea. So if you think about a monitor that is a deterministic automaton, following a path in a deterministic automaton, that's easy. You can store the automaton in a hash table, and then given a state, reading some action, we know how to continue. Here we don't directly know how to continue, or we have in the recursive descent with the phi at side, then we call the function using this guy, then we do a recursive call into the left branch and into the right branch. The right branch is a conjunction, and so on. So this is costly. So it seems much more reasonably that one uses some kind of automata theoretic approach. So we synthesize an automaton, and monitoring means just stepping through the automaton. It sounds much more efficient. So the question is whether we can synthesize an automaton following this approach. Well, we have monitors with outputs, because in a classical finite state machine you have an accepting state, or a state could be accepting or not, or whether it's accepted or not. But here we have a four-valued semantics, so we need 4 output values: true, false, possibly true, possibly false. So the corresponding automata model that are traditional non-input output are Moore machines or mealy machines. Who knows about Moore machines, mealy machines? So who knows about Moore machines? Who knows about mealy machines? Who knows about automata with output? So it's basically very simple. Let's look at an example. What is a Moore machine? A Moore machine is a typical automaton. We have an initial state. We have here two other states. We have Q0, we have Q1. Reading this letter, we stay in the state. Reading the empty set here as a letter, we go to that state, and so on. And rather than having accepting and non-accepting states, every state gets a label, which is the corresponding output. Yeah, so here we have written the states in this form. That's the name of the state, is state Q0, and the output is presumably false. So what is the formula check? It checks P under Q, right? So if you read P, we stay in the current state, everything is fine. If you don't see P anymore, and if you don't see Q, then we have lost, we are output false. And if once we see Q, maybe together with P, maybe just alone, we're happy. And we stay in this state as well. So that's a Moore machine. A Moore machine outputs a wording at the state. When we enter the state, we output the corresponding wording. Yes?
So does that mean that we need here semantics to C1?
No, we are not using Moore machines today. We're using Moore machines tomorrow. We cannot use Moore machines because we don't get semantics for the empty word. So here, once you start, you already have an output. And in our FLTL4 logic, and also FLTL2, we said we don't give semantics to the empty word. So what we're using instead is mealy machines. What is a mealy machine? In a sense similar, we have states, and we also do an output, but we do an output with a transition. So this is also P under Q. As long as we see P, we are presumably false. And once we see Q, we're happy. Then we don't see anything. We have lost. Mealy machines are the right things to use here, because the first output comes with the first action. So we don't have a problem with it. So we have to work. So now we want to translate our procedure eval in FLTL4 to a mealy machine. But actually, it more or less is a mealy machine already. Or maybe let's define. So well, let's recall again. In FLTL4, it gets a letter, it gets a formula, and outputs a logic value, and we get a new formula. So this reads a little bit like, we are in a state, we read a letter, so we are in a state, we read a letter, we output something, and we go to a new state. So if we call formula states, then we basically have a mealy machine. The letter is the input, the logic value is the output, and the formulas are states. In the next state, the new formula depends on the state and the input letter. Output depends on. So let's look at the definition of the mealy machine more formally. We have the alphabet sigma, and it's the input alphabet. We have a finite set of states. We have an initial state. We have the output alphabet. Starting in a state, reading an action, we output the truth value, and we go to a new state. Taking a formula, reading some letter, we do formula rewriting, bringing us to a new state. We do a formula rewriting, bringing us to a new state, and we output the truth value. We can formally define the notion of a run of a mealy machine, but I think that's not so important for now. Well, there is a small problem with the idea, which is, which you can see here. No, you cannot see it here. You can see it here. If we so we start in some state, we read some letter, we output something, and we go to a new state. The new state is a Boolean combination of states that we get here. But it's like a disjunctive combination. Now this is what you know under the term non-deterministic. If you read, if you're in some state Q, you read some A and you might go to Q1 or you might go to Q2. That's what you know under non-determinism. And you could write it in the following way. You have a transition function delta starting in Q, reading an A, you go to Q1. Typically you're used to write a set of states. You can choose which state to follow, but you can also write it like that. You go to state Q1 or to Q2. And if you do that, then you can say, well, what should I write? Or I could also have something like with a B, I go to Q1 and Q2. And what you get there is, so this is like a non-deterministic machine, and here we have a universal machine. Non-determinism means continue in Q1 and accept the word, and it's fine. Or continue in Q2 and accept the rest of the word, and everything is fine. For a universal automaton, the idea would be continue in Q1 and accept the rest of the word, and continue in Q2 and accept the rest of the word. Both passes have to be accepted. And so we have this disjunction of states, which is like non-determinism. And conjunction of states, which is like universality. And of course, you may combine both ideas. So, okay, you should go to Q1, or if that does not work, check Q2 and Q3. And that is what we call alternation. So, if you're in this state, you read some A, you might continue this state or in that one. So, now we go back to Miller machine. So in some sense, what we have written there is a kind of Miller machine, but it's practically an alternating Miller machine or deterministic Miller machine. So we distinguish in general different machine types: deterministic, non-deterministic, universal, and alternating machines. What we need for FLTL4 is an alternating Miller machine. So how can you think about an alternating machine? So you start in Q0, and if you read the empty set or the letter consisting just of Q, your output will presumably be true. And if you read something else, your output presumably false, and go to this state. Well, this is not a state. You go to this state, so you stay Q0, but you also check these other guys simultaneously. And from both positions on, you have to accept. What does it to accept? We have output values of the metrics. Well, if we have the conjunctive combination of the states, we take the mean of the output values. Yeah, so we follow the execution in the tree representation that we get by this state, and we combine according to the output values according to the conjunction of the mean of the joint interpretation that we have in the automaton. Let's look at an example. So we read the empty set, we output presumably false and stay in Q0. Now reading P, we go to Q0 and to Q1, and the output here is presumably false. Now we continue reading, what do we read? We read Q. So here, we were in Q0, so we continue here and we reading this Q, so we output presumably true and go back to Q0. And we were also in Q1. We read Q here, so we stay in Q1 and output also presumably true. Now we read the empty set. So reading the empty set means we take the cycle here and output presumably true. But we also we're in Q1, so we have to read this empty set here. And here the automaton tells us to go to false and output bottom. So we take the mean of presumably true and false, which is false. And I will continue. So formally, an alternating machine is a mapping that gives me, takes me from one state, reading is selected to positive Boolean combination of states, meaning we have states true and false, and we have disjunction of states and conjunction of states. And look at an example, something like A and B or A and C. There are these special states, true and false, but I think I'm not going into detail right now. Find that you have a rough idea. And we could define alternating Mailing machines that are pretty much the same as deterministic Mailing machine. The only difference is the transition function. And it's also that we don't have a single output alphabet, but we have an output lattice. Yeah, because we have to combine output values, so it's not a single alphabet, it's a lattice. But the main difference is the transition function. Starting in a state, reading an action, we go to a Boolean combination of states and output values. Now we could of course say, why do we have a Boolean combination of output values? We could just shorten the definition and take the Boolean combination and return the output value directly. So we could also understand the function as taking a state, reading an action, we output one value and go to positive Boolean combination of states. So that fits to what we've seen in the example, but it does not really make a big difference. Okay, so I think I'm going to skip this. So that's a formal definition of how such an automaton runs. But I think we don't have to understand it in detail. I think it's enough that we understand the idea for the method. So we take a positive Boolean combination of states as our set of states. So we have a set of states with formulas, and we take the positive Boolean combinations. In general, the set of positive Boolean combinations is infinite, but we can identify many states. So we can put the states into, let's say, something like conjunctive normal form, and then we can translate and alternate the real machine into a real machine. Okay, I think this is here, so that's fine. Could also translate it into a universal machine. I think that's not so important. So how do we translate now a given formula into a monitor? So we had our eval until 4 procedure, which takes a formula in negation normal form and takes a letter and returns the truth value and a new formula. So we can interpret that as a transition function of an alternating Wheeler machine. And what is the initial state? Well, the initial state of this automaton is the formula that we start with. It's the formula that we want to check. So the initial state is fine. All subformulas of phi, more specifically the right combination of subformulas, all subformulas of phi are the states. Because whatever we do, when we do a rewriting, we come back to a positive Boolean combination of subformulas. The formula itself, if you read it with or and and, it becomes longer. But we understand now the and or as the combination that we have in our automaton, and so we come up with a Boolean positive Boolean combination of subformulas of our phi, so that is several states. So if we're in a current state psi, we read a letter A, and the output is what we get according to the semantic function, or what we get according to the eval function. And the next formula is this phi prime, that what is given by eval method. Basically the if we are in state true, we read an A, we output top and go to true. If we are in state P and we read an A, we check whether P is an A. If so, we output true, top and go to state true. Otherwise, we output bottom and go to state false. What about the conjunction? Well, or disjunction. If we are in state psi1 or psi2 and we read an A, well, the automaton can choose whether it wants to verify psi1 reading the A or whether it wants to verify psi2 reading the A. Same with the conjunction. Here we see a positive Boolean combination, disjunction version, conjunction version. If we want to, if we are in state next psi1, we read an A, well, we go to state psi1 and output presumably false. The until stuff, that's again easy, just the other way. Okay, we could go through an example briefly. If we want to verify globally not P or next globally Q, well, we have to verify not P or something. So now globally unwinds to, we have to verify the inner part and the globally formula. So we reading something, we go back to the very same formula. That is chopping off what we're starting next. And we have to verify the inner part. So if we see P or something like that, we have to verify I think this should be or, right? We have to verify the inner part. No, sorry, this is the end. This is the end for unbinding this globally. Anyway, so what is the main message? Well, it could generate deterministic monitor and so on. by just translating the alternating automaton, and one can look at the complexities. So we can do formula rewriting using this our eval procedure. That means we have to do a lot of memory management with our formulated runtime. We can translate that into an alternating automaton and then just run the alternating automaton. But of course, we do very similar workload. But we can translate the automaton into a deterministic version, and that means that reading some letter, we go into a subsequent state. So we can process the word that we read quite quickly. So we can basically select whether we want to speed up the verification process. And of course, going from an alternating machine to a deterministic one could mean that we have a double exponential blow-up. As always, we eliminate one. If we go from non-determinism to determinism, we have an exponential blow-up. Same for universality to non-determinism or to determinism. And from alternation, it's also so from alternation to non-deterministic to deterministic, it's an exponential blow-up. So we basically get a state sequence checking our word. So what is the conclusion for today? So every two-value logic is not impartial. Impartiality implies that we have to use several truth values. Several truth values, we have to know, we have to come up with a notion of multi-valued logics with the right notion of truth domain. We consider distributed de Morgan lattices, and we consider this guy here for giving an impartial semantics to LTL. The main difference is that the next operators are treated in a different way in case that we are at the end of the word. Then we have a left to right, letter by letter rewriting procedure defined, and it can be translated into real machines, into an automaton. So the runtime verification conferences, we have sometimes these discussions whether it's better rewriting or automata-based approaches, and my answer is automata-based approaches are always better, because you do the rewriting a priori. Yeah, so if you take a formula and read letter, and the letter do the rewriting of the formula, okay, you can do that at runtime, or you can create the automaton, meaning you check, you're in the initial state, what is the state that you go to with an A, with a B, with a C, and then you continue, and in this way you build up an automaton. And then you have done the automaton, you can store the automaton, because it's faster for monitoring, but of course you have to do kind of pre-computation. Do you know the search algorithm by Knuth, Morris, and Pratt? Not check it on the web. It's I think it's used in these grep tools under Linux. So you can present a regular expression, and then it does some pre-computation to find the corresponding substring in the long text. And it's a very similar idea. Rather than processing the search string directly, they do a pre-computation. They translate it into an automaton, and then they use that to find it. It's very similar to what we do here. Okay, that's enough for today. I'm sorry, I took 4 more minutes than anticipated. But we are talking about anticipation anyway tomorrow. Okay, thank you.
Okay, so welcome to the class. This time shut up. Waiting for us a little bit outside the campus to work together. We'll keep it there.
Let's take this one.
No camera.
Yeah.
La otra vez entró.
The first choice.
I asked about your question.
The gist of it is that these teaching mathematics. Here. It's most of the work is happening in Australia. Teaching is 3 years. Yes, I just make the basically yeah, it's not 8 source, but